So now we're going to go back in Chapter 4 and look specifically at alkanes and cycloalkanes. In this video we'll just deal with alkanes and their different conformations. So alkanes are hydrocarbons composed of only carbon and hydrogen. We can have saturated alkanes where we have only sigma or single bonds. And then we have alkenes, which have double bonds, and alkynes, which are triple bonds. And so typically when we have alkanes that have only single bonds, they are referred to as aliphatic hydrocarbons because of their physical properties. And when you have higher members of this class with 18 or more carbons, they resemble the fat chains of animals and plants. And so in a previous video we looked at nomenclature, so that's section 4.2, and now what I'm going to go through is 4.3, the constitutional isomers of alkanes. So in class I have not explicitly lectured on this topic, but we have looked at constitutional isomers, and if you remember, constitutional isomers have the same molecular formula but a different connectivity of atoms. It's important to realize that constitutional isomers are different compounds. They have different physical and different chemical properties. Okay, so in identifying constitutional isomers, use your IUPAC rules. And as the molecular weight of an alkane increases, the number of possible constitutional isomers increase. So something that's C4H10 versus C6H14, the C6H14 is going to have more isomers. Now, if we move on to 4.4, we can look at the relative stability of alkanes. So alkanes lack polarity, and they are held together by weak dispersion forces, induced dipole-dipole, or van der Waals or London dispersion interactions. And so the boiling points of alkanes are lower than those of almost any other type of compound with the same molecular weight. In general, for both the boiling and the melting points of alkanes, it's going to increase with molecular weight. So here I have butane, pentane, and hexane. So which one would have the highest boiling point or melting point would be hexane, because it has the highest molecular weight. Now alkenes that have 1 to 4 carbons are gases, so think about methane. Okay. Alkanes that have 5 to 17 carbons are colorless liquids. Hexane, for example, you'll work with in the lab, is a liquid and it has 6 carbons. And high molecular weight alkanes of 18 plus carbons are white waxy solids. Think fats. Now, as I said before, constitutional isomers are different compounds and they have different physical and chemical properties. As we increase the number of branch points for an alkane, the boiling point and the melting point will decrease. So for example, here I have hexane with 6 carbons, and here, so here's hexane, I have 1, 2, 3, 4 in the parent chain, 2, 3 dimethyl butane. Both have the formula C6H14. The branched alkane will have a lower boiling point. and this comes from the dispersion forces that hold alkanes together. Hexane chains can pack very nicely and have maximal contact. Here the surface area is reduced, so you pack less efficiently. We have less intermolecular interactions, so this one has a lower boiling point. Now, if we look at the stability of alkanes, we can see that alkanes are quite unreactive towards most reagents. And this is a behavior consistent when we have a nonpolar compound that only has strong sigma or single bonds. Now, under certain conditions, we can have them react with oxygen and the halogens chlorine and bromine. Here, the oxidation of alkanes, this should be O2, to give carbon dioxide in water is the most economically important reaction. So this reaction is used for heating. And the reason that it's used for heating is that when you oxidize a saturated hydrocarbon, we produce carbon dioxide and water, and these products are lower in energy than the starting alkane. So therefore delta H is negative and heat is released, and this heat, called the heat of combustion, is used as a source of energy. So if we have two alkanes with the same molecular formula, C8H18, and one is a straight chain octane and the other has increased branching, so let me draw the straight chain octane first. Here's our octane, and then I'll draw 2,2,3,3 tetramethylbutane. So again, both have 8 carbons with 18 hydrogens, but here we have a highly branched alkane. Now, if we were to burn both of these or oxidize them, and we would measure their heats of combustion, we would see that they would have different heats of combustion. The branched alkane would have a less negative delta H. And what this means is that less heat is released upon combustion. And so, the branched alkane is more stable. So we need to remember that as we increase branching, we are going to decrease the boiling point and the melting point. And as we increase branching, we increase the stability of the alkane. Now in class, I talked about gasoline. And so gasoline is a mixture of C6 to C12 hydrocarbons. And the quality of a gasoline is often expressed in terms of an octane rating. Now a branched alkane will burn more smoothly. Think about it. A branched alkane is more stable. And so it combusts more smoothly. It's not as explosively reactive. And so isooctane, which is a branched alkane, 2,2,4-trimethylpentane, has an octane rating of 100, and heptane has an octane rating of 0. So if we were to draw these alkanes, so 2,2,4-trimethylpentane and heptane, which has 7 carbons. So this has a lower octane rate, has a higher octane rating because it's more stable. And as you increase the octane, so as you go from unleaded to premium, you're increasing this ratio of the branched alkanes to the unbranched alkanes. And the idea is that when you have more branched alkanes, you have less knocking. And so knocking is the pinging sound that you hear upon premature burning of gasoline. And the compounds that will prematurely burn are these straight chain alkanes. Alright, so now we're going to go through sections 4.6, 4.7, and 4.8, and we're going to look at the conformation of alkanes. So when we draw a bond line structure, or we write out the condensed formula, we find out about the connectivity. But these are one-dimensional representations. And we know that we live in a three-dimensional world, so we need to find a way to represent the three-dimensional shapes of molecules. Now, if we have two or more carbons in our alkane, we can twist them into a number of different three-dimensional shapes. So we are not changing the connectivity here. What we're doing is we are changing the arrangement in space. And so this will result in different conformations. Okay? And so we can do this because we can rotate around carbon-carbon single bonds. Now, the conformation of the alkane depends upon the energy of that conformation. And when we introduce different conformations, what we can do is we introduce strain in the molecule. And this is going to dictate the three-dimensional shape. Strain is a measure of energy stored in a compound due to structural distortion. So if we perturb the optimal three-dimensional arrangement of atoms, we're going to put strain on the system. And there are three types of intramolecular strain: torsional strain, steric strain, and angle strain. The angle strain is going to come into play when we look at our cycloalkanes in the next class. And so primarily we're going to look at torsional and steric strain here. So now we need a convention for drawing molecules three-dimensionally. So here I have, if we count 1, 2, 3, 4, we have a butane, and there are 2 chlorines, so it is 2, 3 dichlorobutane. And I have here a solid wedge and here a dashed wedge. And what you can see is that when you have a solid wedge, this indicates the bond is coming towards you or out of the plane, and the dashed wedge indicates the bond is pointing away from you. And so now let's focus on looking down the C1, C2 axis. And what we can do is we can make a Lewis structure. A Newman projection. And it should be the C1, C2 axis because we only have 2 carbons here. Oh no, sorry, it's butane, so again, it's the C2, C3 axis. And if we were to do this, what you would see is that where these 3 bonds intersect, that is C2, and the circle represents C3. And then we need to make the groups that are attached. So we can put the Cl, CH3, and the H, because those are all attached to carbon 2, and then off the back carbon we have a CH3, a Cl, and an H. If you notice here, I have the chlorines, okay, 180 degrees from each other. And we'll talk about this, but this is called an anti-conformation. And so this is a more complicated case where we actually have more substituents. What we're going to do is we're going to start with ethane. And so with ethane, we need to look down the C1, C2 axis because we only have 2 carbons in ethane. Okay, and what we would see is that there are 2 conformations of ethane. Okay, so let's draw them up here. So here is ethane. Okay. And so there's C1 with 3 hydrogens And then we have C2 with 3 hydrogens. Now, when we do Newman projections, what we're doing is we're going to keep the front carbon, leave the front carbon alone. And then we are going to do rotations of 60 degrees. And there are an infinite number of rotations, but when we rotate by 60 degrees, we reach the maxima and minima conformations. This 60 degrees is called the dihedral angle, and it's defined as the intersection of 2 planes. A plane is defined by 3 atoms. So typically what we're doing is we're looking at the difference, okay, here. So here would be 1 hydrogen, and here would be the other, and the dihedral angle here is 60 degrees. Now, when we do another 60 degree rotation and we go clockwise, what happens is that this hydrogen moves down. We're going to keep the front carbon, leave the front carbon alone. And so now what happens is that the angle so we left the front carbon alone, we moved the back carbon. Okay. If we were to look at the dihedral angle between, it's hard to show in this structure here, but if you were to look at the, let's just make this black again, the dihedral angle, what you would see is that you've moved 60 degrees. So now these hydrogens are separated by 120 degrees. Okay, but if we were to look at the angle between these 2 hydrogens, okay, it would be 0 degrees. Essentially, the hydrogens are eclipsed. Okay, so that they perfectly align with each other, and this is going to introduce strain, so that when we have an eclipsed conformation, we have strain. Specifically here, it's torsional strain. Now, the roots of torsional strain are debated. All you need to know is that essentially it's strain due to electron repulsion. The bonds are all aligned. And so if you look below, what we can do is we can make the different conformations of ethane and represent them on an energy diagram. Now, your starting point is relative. What then you need to do is do the rotations according to your starting structure. So if you remember in class, I started with the anti-conformation. But here I have a picture starting with the fully eclipsed conformation. It doesn't matter where you start, you just have to do your rotations according to the first structure. And the idea is that you realize when the bonds are completely aligned, that's high energy because you're eclipsed. And when they are staggered like this and separated by 60 degrees, you're staggered and are lower energy. Now, I'm not going to have you be responsible for the exact difference in this energy. It is 12 kilojoules per mole. The idea is that there are 3 eclipsing bonds. So each eclipse bond contributes 4 kilojoules of torsional strain. What you need to show is the relative difference. Okay. Now, if we were to do this, I'm not going to do propane. Propane's done in your book. I will go through butane for you. So here's butane. We have 4 carbons, 1, 2, 3, 4. There are 2 hydrogens on C2 and 2 hydrogens on C3. What we do now is we look down the C2, C3 axis. If we draw carbon 2, we have a methyl group, which is represented by carbon 1 and 2 hydrogens. Carbon 2 has 2 hydrogens and a methyl group. If you look, I've drawn a staggered conformation where the dihedral angle between all the substituents is 60 degrees. The methyl groups are 180 degrees from each other. This is called the anti-conformation. It is the lowest energy conformation of butane. There is no torsional strain. And here, because we have bulky substituents, there is no steric strain, because everything is separated from each other. The other conformation, the other staggered conformation of butane is called the Gauss conformation. Here, the methyl groups are separated by 60 degrees. There is no torsional strain because we have no eclipsed bonds, but there is steric strain because of the bulkiness of the CH3. We can also have eclipsed conformations of butane. The eclipsed conformations of butane come in 2 forms as well. When we have the 2 methyl groups separated by an angle of 0 degrees, this is the fully eclipsed conformation. The angle here is 0 degrees. This is the highest energy conformation. We have torsional strain because the bonds are eclipsed. We also have steric strain because of the methyl groups. If we were to draw the other eclipse conformation, again, notice in all of these I'm keeping the front carbon the same. Oops. here, the methyl group is eclipsed with hydrogen. So we have torsional strain, but we have no steric strain. Or reduced, let's change that, reduced steric strain. So I'm going to step you through these rotations and then draw an energy diagram for butane. So I know in class I started with the anti-conformation. Here I'm going to start with the fully eclipsed. So you can see the different perspectives and learn how to do this. So here's our front carbon of butane. Okay, so this is fully eclipsed. I'm going to call this is the max energy, and I'm going to call my starting point 0 degrees. I'm going to rotate the back carbon, so we are going to follow the position of this methyl group and these hydrogens. Front carbon the same. CH3, H, H. Okay. This is going to be 60 degrees. This is my gauche conformation. I have steric strain from the methyl groups. Next, I'm going to rotate another 60 degrees, keep my front carbon the same. Here I have an eclipsed, and this is 120 degrees. Next, I'm going to rotate. So again, if we're just tracking things, these are the groups that I'm rotating. Keep the front carbon the same. Here I come to the anti-conformation. These are the groups that rotated. This is 180 degrees. And also my methyl groups are 180 degrees from each other. This is the minimum. There's no torsional strain and no steric strain. If I rotate again, so here we have the rotation at 240 degrees. We have another it's 240 degrees. We have another eclipsed conformation, but this one, I'm just circling the groups that rotated, is not as high in energy as the fully eclipsed. I'm keeping the front carbon the same in all of these projections. Here we're at 300 degrees, and we have another gauche conformation. There's steric strain here, and this is the group that rotated. And finally, we get back to the beginning. Where we are fully eclipsed at 360. Okay, if I was to draw an energy diagram to represent this, here's theta, or the dihedral angle. I start with 0, 60. Let's see if I can just move this up a little bit. $120, $180, $240, $300, $360. We have energy on the Y. Remember to label your axes. Okay. So we said 0 was the fully eclipsed, so that's going to be our highest energy. 60, we got to the gauche. 120, we were eclipsed again, but not as high as the fully eclipsed. 180, we were at our minimum. 240, again, we were eclipsed, but not like the fully eclipsed. 300, we were at the gauche again. Finally, at 360, we were back to the beginning. So here would be the gauche, anti-gauche. The gauche are equal in energy, and here we are partially eclipsed. So this ends our discussion of conformations of alkanes. You'll have to extend this technique to other alkanes that might have more than one substituent.